Everybody, Thrasher here. We are looking at a specific type of force that is applied when objects are submerged in a liquid. We already learned about the pressure that liquids exert. Well, pressure is related to force. We call this force from a liquid or any fluid something known as buoyant force. So we're going to introduce it, kind of see where it comes from, and look at how it applies. In the next video, we're going to look at some more applications about how things like might be sinking or floating or rising up in a fluid, okay? Before we get into this new topic, just real quick reminders about a handful of things. First, let's remember, we learned already an equation for pressure. Pressure is force divided by area, okay? So force and pressure are related. It has to do with how spread out or how concentrated that force is. That's what determines pressure. Also, we learned an equation for density. Density is that lowercase Greek letter rho, and it's based on the mass of an object, how many kilograms, divided by the volume. And you would plug in right here, if it's a sphere, the volume of a sphere. If it's a cylinder, the volume of a cylinder, Okay, we'd plug that in right there. Also, team, we learned the pressure for a fluid. The pressure of a fluid, I'm going to change colors again. P for pressure, okay, same pressure right here. It's equal to the density of the fluid times G, 9.8 here on Earth. Also, it's based on H, the height. So, liquids, just because they're here on Earth and that the weight is stacked against it, adding a pressure also means, jumping back up to this equation, that in a given area, there's also a force that comes from that pressure, okay? Also, number 4, team, no equation, but just a reminder, when we're dealing with fluids, liquids, for example, I think I give the example of, like, imagine splashing your hand or moving your hand in water. You might be moving your hand in one specific particular direction, but because fluids, the atoms and molecules are not tightly connected, they all push and start moving against each other in all different ways. It's wrong to think of pressure as only acting downwards or only acting inward. There's a couple of cute little images that I found online. Like if you have a bag of liquid, okay, maybe a plastic bag you filled up with the sink, if you start poking holes in it, there's pressure that's going to be pushing on the water in all different directions, not just downward. If you have some holes poking up above and on the sides, pressure is going to push out on all those things because the particles, even if maybe in an idealized sense they might feel a force individually at one point in one direction, they keep hitting and bouncing and colliding and moving in all directions at once. So pressure is acting in all directions, inwards, outwards. Again, a diver going in the water, they're feeling a pressure from the water, but not just downwards, not just left, in all directions acting on them. It's acting inwards, we might say. Okay? So that's a core key idea. Okay. With that in mind, let's now look at specifically the pressure or the force of an object. To be honest, I'm really going to be focusing on the force acting on an object, but how we figure out the force does come from pressure because, again, as just another quick reminder, the pressure, it's something new. The pressure coming from a fluid, it's based on the density of the fluid multiplied by G multiplied by the height. Okay, my pen action was a little slow. Okay, with this in mind, to be honest, there's absolutely going to be pressure and therefore forces on the sides of these containers. I actually wish I maybe changed to a different color because I already have a couple labels in there labeled H, which I'll talk about in a second. It's true that water molecules are hitting this left side of my cube that I have in here. But also, remember, there's just as many molecules hitting on the other side, on the right side of the cube. So yes, there is pressure coming from this left side and the right side. There are forces from those sides, but those are going to end up canceling out, okay? The pressure does not matter based on left or right. It doesn't matter on the horizontal direction. So yes, there is, but they cancel. So if I was looking at like the net force in the horizontal, it would be 0 in this case. However, what we learned is that the pressure is going to be different when comparing the top and the bottom. We learn from this equation, top right, that the pressure increases with height. So there is more pressure. There's a reason I drew a larger arrow. There's the reason there's more pressure on the bottom than on the top. It comes from this equation right here. And again, because pressure is equal to force over area, the force that's coming from the water, that's based on the pressure and the area. Now, the cross-sectional areas are the same, but because there's going to be a different amount of pressure, P, there's going to be different forces on these two. So if I want to look at the overall force, I have to take into account that the force from the top or acting on the top is going to be different, and in fact, it's going to be smaller than the force from the bottom, okay? Well, here we go. The overall force, that's what's called the buoyant force, okay? So I'm just going to jump down to writing like FB for the buoyant force. It's based on two. It's whatever force is acting from the top and the force acting on the bottom, okay? Now, the bottom force is larger, so the overall force we're going to be subtracting. And I'm going to subtract the bottom, the one that's going to be pushing upwards, from the top. So I'm going to do, sorry, I maybe should have used two different letters, but I'm going to say maybe F bottom minus F top. Okay? There's forces on both ends, but based on this pressure equation, it's different. So the force is different. Well, okay, the force from the bottom, that's going to be, if I look right here, it's going to be the pressure on the bottom of the cylinder, or on the cube, excuse me, okay, multiplied by the cross-sectional area minus the pressure at the top times the cross-sectional area. I have A's on both sides of my equation, so I can actually pull that out. I can factor it out. So I have P bottom, the pressure on the bottom, minus P, the pressure from the top. Okay, that's where I am right now. Well, let's go one step further, everybody, okay? I'm right here. I'm going to jump over here to keep on writing, but P, pressure, that's this, the density of the fluid times G times H. So I have right here, I have still that A, because that's still this thing right here, multiplied by the density times G times H. Now, H is how high up the liquid is, how deep it is. The bottom cylinder, that's what I labeled right here. This is H bottom. The height, the depth is going to be this H bottom right there, minus the density of the fluid times G times H. The pressure on the top comes from, or it's based on the height at the top, just like that, okay? Now, team, I'm also going to factor out both of these rows, those are densities, and G is the same. So I have A times rho times G, and then that's all being multiplied by H bottom minus H top. All right, with me so far? Oh man, sorry everybody, I bet that was a little jarring. What I just did was I got rid of a little bit of stuff up here relating force and pressure, and then I shifted everything up and to the left. I needed a little bit more room. So where we are, I was comparing the two forces on the top and bottom, and then after plugging some things in and rearranging, this is what I have. Notice what I have in parentheses, the height from the bottom compared to the height at the top. And I'm subtracting. So I'm taking this chunk and I'm subtracting that chunk. Everybody, do you see what that's leaving us with? When I do this minus this, I'm left with this. This is simply the height of the cube. So one last step here, I'm going to go A multiplied by rho times G. I just have whatever the height of the cube is. Okay, I'm almost done. Everybody, A is the cross-sectional area. H is the height. We talked about this before. Okay, the volume of an object, it's based on the cross-sectional area times the height. So I have A and H here. That's the area of the cube and the height of the cube. Really, that's the volume of the cube. So that's going to be, ready? It's going to be rho times G times V. And just because classically this is often rewritten in a slightly different way, I'm going to come right here and I'm going to finish up. The buoyant force, the force that's acting on an object, it is equal to the density of the fluid multiplied by the volume of the object multiplied by G. And team, again, because there's more pressure on the bottom, there's more force from the bottom, there's more force upwards. This turns out to always be an upwards force. There is an upward buoyant force on objects in fluids, okay? This is how it looks on the AP equation sheet. Let's maybe just make sure we highlight a couple of things. Again, this buoyant force is going to be an upward force on any object, okay? On any surface of a planet, okay? Earth, Mars, whatever. Rho, we got to be a little careful here because it's a little confusing. Rho, that's the density of the liquid, okay? It's not the density of my cube right here. It's not that. It's the density of the liquid. Excuse me, I jumped too far ahead. V, however, the volume, it's not the volume of the water. It's not the volume of that container, it's the volume of that object that was under the water, okay? On the slide before, which I'm about to go back to, it says the displaced. We'll talk more about displacement in the next video, but remember how we got this volume. We were looking at the depth of water, H, and the cross-sectional area, okay? That has to do with how much space this cube, or whatever your object is, how much space it's taking up. So it's not the whole volume of the container. That's not V. V has to do with how much volume the shape is occupying, okay? And then G is the easy one. G is just that 9.8. So the buoyant force is based on the density of the liquid, the volume of the object that's in the liquid, and G, 9.8, okay? So what this equation is really showing is that if I want to increase the buoyant force, which is an upward force, I'm going to maybe say out loud, I'm sorry I don't have a picture, like have you ever been in the swimming pool and you have like, I don't know, like maybe a volleyball or a basketball or just some rubber ball, and what do? You hold the ball under the water, you let it go, and what does the ball do? It launches, or at the very least, it rises upwards, right? Of course, things rise upwards in water, okay? Especially if things are, fairly light and they have a lot of volume. They're rising up because there's a buoyant force that acts on them. And that buoyant force is based on how much volume they're taking up. This picture, sorry, it's not a great one. Oops. This is representing some Play-Doh. Oh man, I might get sued by Play-Doh. Play-Doh, if you just take a ball of Play-Doh, wad it up into a ball, put it in water, it's going to sink. But if you have a wad of Play-Doh and you shape it almost like a boat, oh man, that's leading us into our next video. You increase the volume. If you make the volume bigger, that's going to make the upward buoyant force that's acting on that Play-Doh bigger. To be clear, there is still a buoyant force on my ball, but because it has less volume, it's a smaller force. If you make the volume bigger, the force is bigger, okay? And oh man, this leads to some interesting questions about why are some objects floating? Why do some objects sink? Why might they be suspended? Maybe you've heard of this idea that density is what determines things floating. We're going to be talking about that in the next video. But this one's getting long enough. My last slide is just, okay, we have one more force in our arsenal, one more tool in our tool belt. We're used to setting up Newton's second law. So here I just have, I'm not going to work through any numbers or anything, a basic setup. Nothing about the past forces we've learned about has changed. So here I have an example. I have like maybe this big container of water, and I have a metal sphere that's in the water. Maybe it normally would sink to the bottom, but there's a string connected to it. And the question is asking to draw a force body diagram in FBD and set up Newton's second law. If you want, you could hit pause and try it on your own. If we think of the forces acting on it, there's still weight. Nothing is going away from things that we already learned. There's still a weight force, okay? Maybe I should draw this dot a little bigger just because we're going to have a few forces pointing in the same direction. There's not really any forces pushing left or right. To be honest, maybe you could say, well, I mean, doesn't the water push a little bit left and right? Sure. For the most part, though, no one expects you to make little forces horizontally. We know in a fluid they're going to cancel out, okay? So to be honest, most physicists are just going to leave them off. But vertically, there are more forces. The tension still applies a force. You can't forget about that. That string is helping to keep the ball upward. So I might put T like this. There's also, everybody, a buoyant force. Anything in a fluid feels an upward buoyant force. Buoyant force is classically diagrammed like this, FB. To be honest, if I was really trying to be careful, maybe I should be making the downward force the same length as my combined two upward forces. Sometimes, admittedly, College Board will ask you to have the lengths make sense. But key idea, there are two upward forces here. And let's set up Newton's second law. Again, I'm just going to do it in the y direction, okay? The sum of the forces in the y direction, let's say that upwards is positive. Well, I have tension plus the buoyant force. It's almost like it's helping. It's helping that string out. Minus the weight, that equals ma, that acceleration in the y direction. If it's in equilibrium, that should add up to be 0. So again, team, there's no numbers here. I can't really go any further, but this is just another thing we could solve for. That equals 0, and we know like that the weight of an object is still mg, and you know that the buoyant force is rho v times g. So maybe you might have to plug things in like this to get values. I don't know. But that's the setup. Still second law is applicable. Still force diagrams are applicable. Just one more force that we've learned about. Okay, thanks a lot for watching. This one's over.